We're starting chapter 20, which is testing hypotheses about proportions. So in chapter 19, we used confidence intervals to make conclusions based off of a population parameter. And now we're going to use hypotheses and hypothesis testing to do a similar thing, but in a different way. In statistics, a hypothesis is really not much different than a hypothesis in science. So in science, a hypothesis is something that you're going to test. Same thing in statistics. It's just a little different because we're using data instead of whatever you're using to do an experiment in science. So just like in science, in statistics, hypotheses are working models that we adopt temporarily. So a hypothesis is what we're using working under the assumption that it is true, and then we're testing to see if we can determine if it actually works or not. Sticking with statistics, our starting hypothesis is called the null hypothesis. Null means nothing, so nothing interesting is happening, there's nothing new, nothing out of the ordinary. We denote our null hypothesis with H sub 0. So if you see H with a subscript of 0, that's your null hypothesis. And what it is it specifies a population model parameter of interest, and it proposes a value for that parameter. It's usually going to be written down in the form of H sub 0 colon, and then your parameter equals whatever the hypothesized value is. Since we're dealing with proportions here, our parameter, to simplify it, we would just use a P, and it does not have a hat on it, so it's just plain P because it would be the population parameter. And then that would be equal to some percentage or decimal. The alternative hypothesis, which is denoted H sub A, contains the values of the parameter that we consider plausible if we reject our hypothesis. So our alternative hypothesis is basically if we end up saying, nope, the null hypothesis is not true, then the alternative hypothesis would be what we would accept in that particular case. So if the null hypothesis doesn't work, we end up going with our alternative hypothesis. The null hypothesis specifies a population model parameter of interest, and it proposes a value for that parameter. For example, we might have our null hypothesis is P equals 0.5. This would be for the chance of heads coming up when you flip a coin, because the population parameter, we would work under the assumption that it's even. You have a 50-50 chance of heads or tails. So we would say 0.5. That null hypothesis is just assuming that the coin works how it's supposed to. It's not weighted, it's completely normal. We then, once we have our null hypothesis, we then want to compare our data to what we would expect given that the null hypothesis is true. So if I were to go through and flip a coin 100 times, and I ended up with 54 heads, so heads came up 54%. I then compare that to my null hypothesis. It's not exactly my null hypothesis, but is my value out of the ordinary? Is it surprising? In that case, I'd probably say no, but we'd have to do the math to find out. If I were to flip it 100 times and I got heads 78% of the time, that might be a little more surprising because that really doesn't match my null hypothesis. So again, once you have your null hypothesis, you want to compare your data to what you would expect given that the null is true. So when we flip the coin, we're working under the impression that it should be 50-50. We compare it by finding out how many standard deviations away from the proposed value we are. Once we have figured out how many standard deviations we are from our proposed value, which is our null hypothesis, we then determine how likely it is to get those results given that our null hypothesis was true. So again, you're always working under the impression that your null hypothesis is true. So a trial is a hypothesis test. Think about the logic of a jury trial. To prove someone is guilty, we start by assuming they're innocent. That's the way our system is set up. It is not necessarily the way the system works, but it's how it was designed. Again, the jury is supposed to assume that the person on trial is innocent. You are supposed to be innocent until proven guilty. So they are working under the assumption that they are innocent. We retain that hypothesis that that person is innocent until the facts make it unlikely beyond a reasonable doubt. Then and only then we reject the hypothesis of innocence and declare the person guilty. So again, you are assuming that the person is innocent until the prosecutor can come up with as much evidence to prove without a reasonable doubt that they are in fact guilty. But only then will you actually reject the assumption of innocence and call them guilty. The same logic used in jury trials is used in statistical tests of hypothesis. We begin by assuming a hypothesis is true. Next, we consider whether the data are consistent with the hypothesis. If they are, all we can do is retain the hypothesis we started with. If they are not, then like a jury, we ask whether they are unlikely beyond a reasonable doubt. Which brings us to p-values. The statistical twist in this particular case is that we can actually quantify our level of doubt. We can give it a value. We can use the model proposed by our hypothesis, so stick with our null hypothesis, assuming that's true, and calculate the probability that the event we've witnessed could happen. So again, my null hypothesis for flipping a coin is that 50% of the time it will come up heads. If I were to do a trial and I got 64 out of 100 heads, I can calculate the probability that getting 64 heads would happen under the assumption that it should be 50-50. It's the probability we're looking for. It quantifies exactly how surprised we are to see our results. This probability is called a p-value. So again, we calculate the p-value, which is a percentage, to find the probability that our sample would occur given our null hypothesis is true. When the data are consistent with the model from the null hypothesis, the p-value is going to be high, and we are unable to reject the null hypothesis. So if you have a high p-value, you are not very surprised, and we are unable to reject our null hypothesis. In that case, we have to retain the null hypothesis that we started with. You cannot claim to have proven it, because you haven't. You just have not proven it false. If we fail to reject the null hypothesis, and that's how we're actually going to declare it, is we will say that we fail to reject the null hypothesis, and we do this when the data are consistent with the null hypothesis. So if the data are consistent with the current model, we fail to reject the null hypothesis. That means that the data are in line with what we would expect from natural sampling variability. So we don't expect it to be the exact value of our null hypothesis, but as long as we can assume it came from natural sampling variability, we're good to go. If the p-value is low enough, we will reject the null hypothesis. So if our p-value is low, that means that we are surprised, and what we observed would be very unlikely given the null hypothesis was true. Again, if I flipped a coin 100 times and 64% of them came up heads, then that doesn't necessarily fall in line with what my null hypothesis said. So I might reject the null hypothesis and say that the coin is not actually 50-50. So what do we do with an innocent defendant? If the evidence is not strong enough to reject the presumption of innocence, the jury returns with a verdict of not guilty. The jury does not say that the defendant is innocent. All it says is that there is not enough evidence to convict. So, in other words, to reject innocence. The defendant may, in fact, be innocent, but the jury has no way to be 100% sure of that. So all they can say is not guilty. Statistically, we will say we failed to reject the null hypothesis. We never declare the null hypothesis to be true, because we simply do not know whether it's true or not. All we know is that we haven't proven it false. Sometimes in this case, we may say that the null hypothesis has been retained, but you will see me always saying we failed to reject. In a trial, the burden of proof is on the prosecution. In a hypothesis test, the burden of proof is on the unusual claim. The null hypothesis is the ordinary state of affairs. That's what we're assuming to be true. So it's the alternative to the null hypothesis that we consider unusual, and for which we must arrange evidence. So we must have evidence to show that the unusual alternative could actually, in fact, be what is true. So let's try just checking really quickly. A research team wants to know if aspirin helps thin blood. The null hypothesis says no, it does not. They test 12 patients, observe the proportion with thinner blood, and then calculate a p-value of 0.32. They claim that aspirin doesn't work. What would you say? In this case, we would say that we failed to reject the null hypothesis. A high p-value means that we are not very surprised, and it is in line with our null hypothesis. Therefore, we failed to reject it. They were unable to show that aspirin was effective. An allergy drug has been tested and found to give relief to 75% of patients in a large clinical trial. Now scientists want to see if the new improved version works even better. So we want to know, what would our null hypothesis be? Remember, your null hypothesis follows what is already known. Null hypothesis, the word null means nothing new, nothing interesting. So in this particular case, it would be that there would be no change. So the allergy drug that's been tested is kind of what we would go with. So we would go with a null hypothesis of p equaling 0.75 because that's where we already are. The new drug is tested, and they ended up getting a p-value of 0.0001. What would you conclude about the new drug? Now, this is a really small p-value and actually shows that we are really surprised. So this p-value provides us strong evidence against the null hypothesis. So in this case, we can reject the null hypothesis and then kind of find in favor of the alternative hypothesis. We're going to keep working with hypothesis testing, but that is all I have for today. So have a great night, and I will see you guys tomorrow.